Hey, hi. Thanks for hanging out with me this morning to chat about MLOps and going from model-centric to data-centric AI. There are some ideas that I've been fleshing out with a couple of my teams, landing AI and deep learning AI, over the past year plus that I hope will be useful to a lot of us in the AI community, hopefully you too, in terms of helping us be more systematic and efficient in how you might build and deploy AI systems. So I want to share those ideas with you and maybe also get your feedback. Here's what I mean. AI systems are made up of data and code. Let me share my slides. All right. So AI systems are made up of data and code. And by code, I mean the model that you might implement in your network architecture, what have you. Excuse me, by code, I mean the model, including the neural network architecture you might choose, that is then trained on the data set. The way that machine learning has developed over the last few decades, a lot of progress has been driven by teams downloading and trying to do better on standard benchmark data sets. And so we spend a lot of time improving the code or the model or the algorithms. And what I'm finding is that for a lot of problems, it'd be useful to shift our mindset toward not just improving the code, but in a more systematic way, improving the data to then help us get the performance you want your learning algorithm to have. Let me start with an example. I'm going to make this presentation a bit interactive, so I'll ask you a few questions that you can answer online in this presentation as well. But here's an example of inspecting steel sheets for defects. This is a project that one of my collaborators, Ivan Joe, was working on. This is a picture of giant rows of steel, a little bit like the rows of aluminum foil you might have in your kitchen, but instead of super thin sheets of aluminum, these are giant thick sheets of steel. So, one of these sheets of steel may be the car door of a car you may drive in the future. It turns out when these sheets of steel are manufactured, it can have different defects like this, like this, like this, like this. And in this factory, there were 39 types of defects that the factory operators wanted to detect using computer vision. If you train a neural network, train a baseline system, well-tuned hyperparameters, you get 76.2% accuracy. And the factory operators wanted to target 90% accuracy because that's how well human inspectors were at spotting these types of defects. And this is important, right? You don't want to buy a car and then find that there's a wrinkle on the sheet of steel that was used to make the door of a car that you're driving or you just bought. So I know I've given you relatively limited information so far, but I want to ask you a question that just answer according to your gut feeling. If you were the one leading this project, given what you know now of the project, 39 classes, so 76% accuracy is not bad. But given what you know now of the project, which isn't that much, if you were leading this team, would you ask the team to go and improve the code, or would you go and improve the data? So if you're watching the live stream, go ahead and go to this URL and pick one of the answers. Just answer your gut feeling. I'm curious what people are thinking, and then I'll share people's share what people are voting for in a second. All right, I'm gonna stop sharing my screen. Cool. Okay, so there are many of you on the AHA slide / MLOps slide voting. All right, I'll take another 5 seconds. I'll share what everyone is voting. Okay, 4, 3, 2, 1. Okay, cool. So this is, all right, wow, okay, over 1,000 of you on this site voting. Okay, so great, thanks all of you voting, right? It's interesting, it's like an 80-20 split. So, the interesting thing to me is that maybe instinctually, right, many of us think we should, we can work on the data to improve the performance, although there's value to improving the code as well. But a lot of the history and culture and DNA and instincts of AI teams to talk about the code or the neural network architecture rather than the data. Let me share with you what actually happened. When Ivan was working on this project, this is what actually happened. 76.2% accuracy was the baseline performance using a model-centric approach, meaning, take the baseline, which is a pretty decent model with reasonable hyperparameter tuning, decent learning rate, decent regularization parameter, Different teams actually went and searched for neural network architectures, go to GitHub, download the latest state-of-the-art algorithm, try that out, different neural network architectures, different models. After a lot of work by multiple teams, this resulted in 0% improvement. There's actually a bunch of models that wound up between 71 and 75% accuracy. It's very difficult to make improvements this way. But using a data-centric approach, in about 2 weeks, wound up getting 93.1% accuracy, a much bigger difference in this project by improving the quality of the data. Now, let me just run through a couple other examples. Solar panel defect detection, look at the solar panel, see if there's a problem with it. Baseline was 75.68% accuracy. Searching for new models, trying different neural network architectures, slight improvements, but improving the data quality, much bigger improvement. And one last example, another surface inspection problem, 85% accuracy, almost no improvement with model-centric approach, and a bigger improvement with a data-centric approach, by which I mean trying to systematically improve the data quality. When I speak with non-tech, when I speak with different people, including especially less technical teams, I found this analogy to be sometimes useful. So maybe it'll be useful for you too, which is I tell people that data is food for AI. And in the AI world today, the way we use our data, it feels like we're like the chef, right? That wanders in the back of someone's kitchen and figures out what's been at the back of your refrigerator for 3 months, maybe slightly leaky, and we just cook that, right? And maybe the food's not terrible that way, but we know that master chef preparing a good meal views it as a critical part of their job to source vegetables, clean the vegetables, prepare the ingredients, and then at the end there is the application of heat to prepare the meal, but that's a small part, important part of their responsibilities. So too it is in AI. For many years, maybe 10, 20 years, we've been telling each other as if it's a joke that, hey, did you know 80% of the work in machine learning is data cleaning, 80% of data science is data cleaning. We say it like as a joke. But to me, if 80% of our work is preparing high quality data, then I think preparing that data is the core part, a core part of the work of a machine learning engineer. Now, the importance of data has been widely discussed, but what I would love to see is a shift toward making the way we approach data more systematic. And that's the importance of MLOps, which I'll talk a little bit more about later. A little bit inspired by this, 80-20 rule, 80-20 heuristic. A few weekends ago, I went into archive, and in a completely unscientific survey, I went and searched for the 100 most recent machine learning papers and skimmed the 100 abstracts of the 100 papers I find. So in this, non-scientific, I don't want to say it's representative, I just skimmed 100 abstracts. I found that 99% of the abstracts I skimmed seemed to be talking about different ways of improving models, and only one of the 100 abstracts, one of the 100 papers, research abstracts I skimmed was on data augmentation in this case, and seemed to be about the data. So if 99% or some large percentage of the research work on AI is on 20% of our actual work, then I think it'd be worthwhile shifting quite a lot of our attention to the other 80% and making that more systematic. One theme you hear me repeat multiple times is how to do this systematically. So in terms of making data preparation systematic, a framework I use is to think about the life cycle of a machine learning project. So here's what I mean. When you think about building a machine learning project, there's usually a lot of emphasis on training the model. And that's important. You got to understand the neural network architectures, you have to understand how to build deep learning algorithms. That's important. But I think training the model, training, error analysis, iterative improvement, that's just one small part of the entire life cycle of a machine learning project. I think of the full life cycle as this. And if you're building a machine learning project, I hope this framework will be useful for you too. First, you have to scope the project. So, decide what you want to work on. Like once I decided to work on speech recognition for voice search, right? Just decide what to work on. Then you have to define and collect the data. Then you have to train the model, carry error analysis. Sometimes error analysis would drive you to go back to improve your data set. And then after doing this a few times, you may then deploy the model in production. And often based on the data you get back from your production deployment, you might decide to go back to update the model or go back to collect more data. This diagram, my thinking on this diagram was heavily shaped by two of my friends, Dylan Laird and Daniel Biberieta. But I hope that this diagram, this framework will be useful for you to think about your machine learning projects as well. Let me step through these 4 steps with an example. Scoping. Say you decide to work on speech recognition for voice search, right? Which I once did, early in my life. So decide how much data you need, how much resources, how much engineering, how much compute. So decide to do that. Next step is to collect data. So in what I'm calling a data-centric approach to AI, one of the most important questions you have to ask is the data labeled consistently? So if it's not just do you have enough data, but also is the data high quality? Let me illustrate that with an example. Here's an audio clip of something very typical audio clip you might get in voice search, right? So let me play this audio.
Today's weather.
Right. So the question is, given this audio clip that you just heard,
today's weather,
would you want to transcribe it like this, which is perfectly fine, today's weather? Or would you want to transcribe it like this, which also seems perfectly fine, using ... or the ellipsis punctuation mark instead of comma? Or would you want to say that, well, there's a lot of noise in audio. Sometimes something may fall down and there's a clunk sound or other noise, and it's just noise. So let's not transcribe that. Let's transcribe it like this. It turns out any of these labeling conventions are perfectly fine. I would probably use the first or the second one, but really any of these will work. But what is not fine is if 1/3 of your labelers uses the first and 1/3 the second and 1/3 the third transcription convention, because then your data is inconsistent and is confusing for the learning algorithm. And this will hurt your learning algorithm's performance. How is the learning algorithm supposed to guess, which of these transcription conventions one of the labelers happen to use? Let me illustrate this with a second example. So one of my friends, Kian Kattenfurush, really likes iguanas. I have an iguana detection example, but this example actually maps well to specific computer vision applications like defect inspection, but are more technical, so just hard to explain. Right? But let's say you want to build a computer vision system to detect iguanas. So you go out into the field and maybe go into the forest or wherever the iguanas are and take 500 pictures of iguanas, and you send them to a labeling team and say, hey, labelers, please use bounding boxes to indicate the positions of the iguanas. So what happens? Labeler 1 says 1 iguana, 2 iguanas, right? Oh, good job, labeler, right? It's a great data set, really helpful for your learning algorithm. Second labeler says, well, the iguana on the left, the tail goes all the way to the right, so I should draw a bounding box around the entire iguana. That's 1 iguana, 2 iguanas. This is the second equally hardworking, equally diligent labeler, can't fault them either. A third labeler says, well, I have 500 images to label. I'm going to use a bounding box to indicate where are the iguanas. And again, hard to fault this labeler either. Again, and it turns out any of these labeling conventions is fine. You can make it work. I would prefer the first or the second to the third, but any of these, can be made to work. But what is not okay is if the 3 different labelers, if different labelers use different labeling conventions, because then your data is inconsistent and this hurts the machine learning algorithm's performance. Now, what I see is that experienced machine learning engineers or inexperienced one will sometimes kind of hack around in the Jupyter notebook and spot this problem and fix it. And this will result in an improvement in the learning algorithm's performance. But the shift I think we should make as a community is, instead of counting on the skill and sometimes luck of an individual machine learning engineer to spot problems like this in images, in audio, or in other problems, I think we should shift as a community toward making the spotting and correcting of problems like these much more systematic. So this is what some of my teams do, and I think hopefully these practices will be useful to you, which is when concerns about a data set, we would ask 2 independent labelers to label a sample of images. and then quantitatively measure consistency between labelers to discover where they agree or disagree. And it turns out in problems with a lot of classes, it's actually not easy to find the one class out of the 39 classes where they disagree to fix that, which is why having tools and metrics to focus your attention on the right parts of inconsistency turns out to accelerate machine learning development. And then for classes or the categories of data where the labelers disagree, revise the labeling instruction until they become consistent. There is a nascent field called MLOps, machine learning operations, that is trying to make the development and deployment of machine learning systems more systematic and repeatable and reliable. It's a nascent field, but I think these are some of the tools that will make a big difference to MLOps. I'll say more about this in a second. But to give an illustration of what a tool like this, or what a process like this can do, this is an example from the steel defect detection that I mentioned at the start of this presentation. Of the 39 classes, one of the classes was foreign particle defects. So sometimes on the sheet of steel, there could be a speckle of lubricants or a speckle of dirt on the sheet of steel. And so we found that one labeler would label it like this: defect, 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 defect. Different labeler will say, well, given these specks of lubricant, specks of dirt, looks like there's a bunch of specks there and there's a bunch of specks there. And it's actually difficult to spot. It's difficult to fault these labelers. They're actually well-meaning, hardworking, trying to show you where the defects are. And we found that if you can go discover this problem and ask labeler 2 to label in a way more consistent with labeler 1 in this case, then the labels look like this. And this has a big impact of the algorithm's performance. So I think in terms of how we can make this focus on data more systematic, for a long time, a lot of AI, a lot of machine learning has had a model-centric view. And I think we're all kind of trained to do this because of the way machine learning research made progress. You download a benchmark data set, and if you can improve the performance on that, you publish a paper. So a lot of machine learning progress was made this way, which is good, right? There's not a lot of bad thing. But in the model-centric view, which is the way a lot of people approach problems today, the view is collect what data you can, develop a model good enough to deal with the noise in the data. And so in this view, you hold the data fixed and iteratively improve the code or the model. In the data-centric view, which I urge you to consider taking, for some of the problems you might be working on as well, you can view the consistency of the data as paramount and to use tools and processes to systematically improve the data quality. And in fact, what I find is that if you have a good enough data set, sometimes there are multiple models that will do well. Go ahead, download the latest state-of-the-art thing that was just published on GitHub 2 weeks ago if you want. But I found for a lot of practical applications, so unless you have good enough data, there are plenty of models. You do need to understand neural networks and you need to understand models. But when you have that foundation, you understand the models, then when you get your data set clean, there are multiple models that can work well. But in this view, you can hold the code fixed and iteratively improve the data. Now, I'm about to ask you another question on our slides, but I found that especially with small data sets, modern neural networks are low bias machines, right? So if you have, less than, 10,000 examples, right? Model-sized data sets, modern neural networks are low bias machines, meaning that you very likely fit your training set perfectly. And so performance problems, the need to improve the performance of your neural network is usually a variance problem. And improving the data set, is just a good way to reduce the variance. So I've alluded to, maybe the importance of these in smaller data sets. Let me ask you another question, right? Go to this URL and I'm actually curious. I have no idea what you'll answer, right? Think about the last supervised learning model train. How many training examples did you have, right? Please enter an integer, right? All right, cool. And then, you know what? I will, let me take another, I don't know, few seconds and then I'll show what people are answering. I'm using a word cloud to show everyone's answers. Not sure that's the best visualization, but okay, I'll show people's answers in another like 5 seconds or something. All right, feel free to keep on answering answers. Cool. Okay, wow. All right, maybe a word cloud wasn't the best visualization I chose. So I think the 10,000 is in the middle because that's the single most frequent answer. But there are a lot of different answers, right? I see on the low end, someone's doing something with 3, 4, 6, 1, 7, 5 training examples. There are a few in the hundreds. I see 250, 50,000, some large numbers as well. All right, there's a one with a lot of zeros there flying around. Someone's 10 million examples, a few people with 5,000 examples. The larger fonts indicates the more frequent answers. 6,000, right? So several thousand, I don't know, 120,000. So there's a huge variance with a lot of answers that are, 10,000 or fewer, but also some, right, in like 10 million examples or even larger data sets. Cool. All right. Wow. Yeah. I think okay. About a couple thousand of you have been submitting answers, so maybe I need to find a better visualization than a word cloud. So I think it's difficult to know. Sorry, can you see this? So it's difficult to know, exactly what is the most representative sample of training set sizes across all of AI. I don't actually know how to get that answer, but talking to friends, my gut feeling is that the majority of machine learning problems actually have, relatively smaller data sets, although there are a few with very large data sets. So in another in a I have to admit, not terribly scientific survey, one of my team members went on to Kaggle, and again, I don't know if this is representative, right, of the AI world broadly, but went on to Kaggle and counted up the number of training examples in the most recently posted trending data sets. And this was the histogram of data set sizes. And there is a large range, right, with the majority of problems with under 10,000 examples, but then also some very large ones with over 100,000 examples. What I see chatting with many friends across the industry is that the problems with the very large data sets tend to get a lot of the PR, especially because AI had grown up in consumer software internet. If you're a large consumer software internet company with, 1 billion users or over hundreds of millions of users, then you have a data set of 1 billion training examples or hundreds of millions of examples, and you use that, and that's great that you have so much data. But especially as AI makes its way into other industries, everything from healthcare, where the number of electronic health records is just much smaller per healthcare system, or agriculture, where you don't have 1 billion tractors, you may have dozens of tractors or dozens of fields, or manufacturing or other industries like that. There are a lot of problems where the training set size is less than 10,000. And there, I think a different set of ideas is helpful for building learning algorithms that can help us collectively break into these other industries. So it turns out that smaller data sets, when you have a smaller data set, label consistency is even more important. So let me illustrate an example. So one of the things I used to do, some of you know, many years ago, I used to fly helicopters using machine learning. Right. And so one of the things you might want to do is input a voltage and try to predict the speed of a motor, or the speed of the rotor, or speed of a motor in a helicopter, in a machine or something. And so here's a small data set with 5 training examples. And this is a noisy data set. And it turns out when you have a noisy data set like this, it's pretty difficult when the data set is small to know what's the right function to fit, to fit this data. It could be, maybe it could be straight line like that. Maybe it's a curve that looks like this, flat, and then, I don't know, maybe it looks like this, right? Maybe it looks like that. I don't know. There are lots of lines that could fit this data. So when you have small data set, 5 examples in this case, and noisy labels, it's difficult to fit a good model. It turns out noisy labels is just fine if you have a lot of data. So if you're a consumer internet company with 1 billion examples or maybe 1 million examples, well, learning algorithm can average out over the noise. So if this data set is equally noisy as that on the left, but because you have a lot more data, you could more confidently, right, fit the curve like that. You kind of just average out over the noise. So that actually works. It works okay, maybe when you have a lot of data. To me, an interesting case is if you have a small data set, but a clean, consistent set of labels. Even though this data set has only 5 examples, same as the leftmost one, because the data set here is clean, you could very confidently fit this curve, right? So even though a lot of the PR and hype in the media is about the giant data sets, and if you have a giant data set, good, use it. It's great that you can use it. I have been repeatedly surprised at how often, I can get a learning algorithm to work with like 40 images or 100 images or just a very small data sets. And doing that, I found is critical to have processes and tools to make sure you have a clean and consistent data set. Let me share with you what the theory says. Let's say you have 500 examples, say your iguana detector, right? So you found 500 pictures of iguanas. And if 12% of the labels are noisy, so incorrectly labeled, then from a theory of information, kind of Shannon information calculation, you can show that the following 2 techniques are equally effective. Option 1 is you can go and find the 12% of data that was mislabeled and clean up the noise. And 12% is not that high. Right? If you have 8 labelers and one of the 8 labelers uses an incorrect or different labeling convention, that's 12.5%. So I've seen a lot of data sets where the label noise is much higher than 12%, right? But so one thing you could do is clean up the noise. So 12% of 500 is 60. Just find the 600, find the 60 images that are mislabeled and clean that up. Option 2 is you can go out into the field with your camera, find another 500 iguanas wandering around the forest, take another 500 pictures, and then get labelers to label your 500 new images to an equally, to the same labeling quality as before. You can double the training set. Turns out from theory information calculation, both of these will be about equally effective in terms of improving your learning algorithm's performance. I would argue that for a lot of problems, it's much easier to go in and find your 60 mislabeled examples and find a systematic way to clean that up than to go out and double the size of the training set and then label it, with a similar level of noise as before. So what I found is that in consumer software internet, if you're 1 billion users, some challenges are cleaning up that data. But in all of the other industries, plenty of problems with 10,000 or fewer training examples, like the numbers that a lot of you entered just now, right, on the interactive website just a couple minutes ago. There's a lot of room for improvements in problems with fewer than 10,000 examples, which I think is maybe the majority of machine learning problems we as a community face today. Oh, and I often use the number 10,000 because that's roughly the range below which is feasible for a machine learning team to basically look at the entire training set. We can look at all 10,000 examples manually, kind of just barely, and so that gives you more flexibility in how you go about analyzing and develop the data. Let me just share with you one more example of this concept. This is a project we're working on with automotive company or automotive components classification. So had a noisy data set where the bounding boxes, slightly inconsistently labeled. And with the noisy data set, this is the performance, accuracy or mean average position as a function of training set size. We found that if you clean up this noise, go to clean data set, then this is the performance. So imagine if you had started off with 500 examples and a noisy data set. If you wanted to get up to 0.6 MAP or 0.6, 60% accuracy, then you could either go in and clean up the data set, or you could, I don't know, shift to the right, and maybe you need to nearly triple, right? Double, triple, go from 500 to, I don't know, over 1,000 training examples in order to get that to a similar level of accuracy. And so this is another example where, my teams found that it's just easier to clean up the data. I've been talking a lot about the importance of these ideas in smaller data problems, but it turns out that even big data problems, but ones where there's a long tail of rare events, those are actually small data problems as well. So take web search. Everyone knows that the large web search engines have a lot of data. But it turns out that web search is a long tail problem, meaning that there are a lot of web search queries that a search engine may see only once today and may never see again, or may not see again for a very long time. So for those rare queries in the long tail, there's actually very little data on them. So those are actually, small data problems. Or self-driving cars. There are lots of rare events that can happen on the road, specific configuration of traffic or a different car doing something that your self-driving car needs to be safe in those situations. And so those rare events are actually small data problems. Also, product recommender systems. If you're a large e-commerce site with millions or tens of millions of more products on your website, then if you have a long tail of products, the products that are rarely sold tend to be ones where you have relatively small data sets. And so even for those big data problems, when you have a long tail, you actually have small amounts of data for the tail. And so some of the ideas I'm sharing today, not all, but many of the ideas I'm sharing today will be applicable as well. So when I'm working on smaller data sets, I found that having tools and processes for the data quality turns out to be critical. And again, I know, right? I'm saying data is important. Well, we've known that for decades, but I think the shift is how do you build tools and processes and make this systematic? Come back to that in a second. Let me keep rolling forward with the speech recognition example. So talk about scoping the project, collecting the data, and now training the model. Let's say that you train a speech recognition system and error analysis shows that your algorithm does poorly in speech with car noise in the background. So, so this is what speech with car noise in the background sounds like, right? So you can hear me talking, and I'm not actually in a car, but it was in a car. Maybe this is what you would hear. So this happened to me. I built a speech recognition system and found that it doesn't do well when there's this type of car noise, like you're hearing in the background. So, all right, let me turn that off. So with a model-centric view, you would ask, how do I tune the model architecture to improve performance? And you can do this. Maybe build a filter to filter out the lower frequencies, which car noise tends to be. You could actually do this and maybe it'll work. But with a data-centric view, you would instead ask, how can I modify my data? Maybe new examples, data augmentation, labeling, to improve the model performance. So what I did was I asked my team to collect more data with car noise in the background and also use data augmentation to synthesize more data with car noise in the background. And that's actually what fixes problem relatively efficiently. Today, some of my friends and I, Kai Yang, Daniel, Bibireta, we routinely go to our teams and say, hey, everyone, the neural network you're using is good enough. The UNet, the RetinaNet, the ResNet, whatever neural network architecture is good enough. So everyone, let's just hold the code fixed. Let's not mess with the code of the neural network architecture anymore. Let's just keep on working in a systematic way to improve the data quality. And let's improve the data to get you the performance you want your system to have. And we found for many projects that when we give that direction to our teams, that this allows the team to make faster progress on the machine learning project. Now, one of the themes I keep on coming back to is how can we make this systematic, right? So not just, an individual engineer hacking around that spots the problem of car noise and decides to go and collect more data with car noise. So toward making it systematic, this is what I tend to do today, which is train a model and then do error analysis to identify the types of data the algorithm does poorly on, such as speech with car noise. And then we would, brainstorm or use, or sometimes even more systematic ways, we'll then ask what type of additional data do you need to improve the performance on that category of data. So you can either get more of that data via data augmentation, data generation, data collection, collect more data, or give a more consistent definition for the labels if they were found to be ambiguous. And it turns out that systematic processes like these of error analysis followed by changing the data. This is important because in machine learning, we always want more data, but for speech recognition, it's not helpful, or it's not nearly as efficient to just say, let's collect a lot more speech data. So having the tools and processes to do the error analysis so that you can, in a much more targeted and efficient way, get more of the data you need, which is more data with speech with car noise rather than just more speech data in general. That turns out to be really important for being efficient in how we improve the performance of our systems. All right, let me move on to production deployment. So when today there are some teams that think that when you finally deploy a project in production that you're at the finish line, and I actually tell teams, no, sadly, when you deploy in production, well, when you deploy in production, you should celebrate that, congratulations, and you may be halfway done with your machine learning project, because when you deploy a system in production, the world will change, concept drift, data drift. So you still have to monitor the performance and deployment and build tools to systematically check for concept drift or data drift that can result in performance degradation, and then find the right types of data to flow back to the earliest stages of the machine learning project lifecycle to regularly retrain and update the model, right? So to engage in continuous learning. And so once again, finding the right data to flow back is, I think, critical. To monitor and flow the right data back is critical for monitoring and maintaining your system when it is in production. Now, you've heard me mention many times how to make this systematic. MLOps is a nascent field, and today, the websites of large companies have different and slightly inconsistent ways of defining what is MLOps. But MLOps is, I think, a nascent discipline that is trying to make the development and deployment of machine learning systems systematic. Let me share with you what I think may be some useful frameworks for you to approach MLOps. In traditional software engineering, we needed code to run. And so there were software engineers that will write the code, and then DevOps teams that are responsible for quality and infrastructure, right? So DevOps is, so after the software engineer, maybe not throws the code over the wall, but gradually transitions the code to a DevOps team. The DevOps team is then responsible for managing the data center scaling, making sure that even if there's a spike in traffic, that the workload on the system, is manageable. If there's a network outage, that things stay up. So that's what DevOps teams do. Good DevOps teams do a great job in maintaining this quality and infrastructure and keeps things running. Now, with AI, we don't just have code, we have code plus data. And so we have these new roles with machine learning engineers building the machine learning models. And then also, hopefully, this nascent discipline to help maintain quality and infrastructure for the data. But there's a big difference, but there's a significant difference between how we deploy machine learning systems or AI systems compared to traditional software systems that implicates how we build MLOps versus DevOps teams. Let me share with you what I mean. So traditional software was, relatively more left to right, feed forward process. We scope a project, develop a code, and deploy in production. And so DevOps teams could be responsible for that. But we've seen that AI software is a more iterative process. We have to develop it. And then there are also these, backward pointing arrows where you have to keep on iterating on the data and training model even after production deployment. So I found in AI software, it works much less well if you train a model and then kind of try to hand it over to a DevOps or MLOps team to just run it for you. Because this stage results in a lot of feedback loops to the earlier stages as well. So when I am standing up, setting up an MLOps team, I think one of the most important things for an MLOps team to do is to support ensuring high quality data through all of these stages of the machine learning project lifecycle. So the textbook on how to do MLOps has not yet been written. No one, I don't think there's like a set of guiding principles on how to maintain quality and infrastructure for machine learning projects. I think we as a community are still figuring those things out. In my view, the single most important thing for MLOps team or for MLOps tools to do is to ensure consistently high quality data throughout the machine learning project lifecycle. There are other things an MLOps team can and should do, but if it just does this one thing, then I think the machine learning development and deployment process can be much more efficient. So during the data collection phase, MLOps teams or tools can help answer how do you define and collect the data so it's consistent. During the training phase, MLOps teams can help with, well, how do you modify the data systematically and efficiently to improve model performance? And during deployment, you can ask, MLOps tools or teams can help figure out what data do you need to track, concept and data drift, and flow the right data back to the earlier parts of the system to improve performance. All right, so I have another question for you. Given this work of an MLOps team to ensure consistently high quality data, I am curious, who do you think is best qualified to take on an MLOps role? And I don't know the right answer to this. I think there's actually no single right answer. I actually honestly don't know the best answer myself. But do you think, oops, oh, sorry, I hit the wrong button. Okay, sorry, if you go back to AHA slides, that should work. Do you think, the MLOps role is best done by a machine learning engineer or data scientist, right? Or do you think it's best done by a DevOps engineer? There are lots of great DevOps engineers. Maybe they can expand their role to encompass MLOps work. Or should it be a software engineer? Lots of great software engineers have become machine learning engineers, and maybe they could do this too. Or should it be the domain expert? So maybe a manufacturing expert should be responsible for the manufacturing data, and a linguist speech expert, should be responsible for the speech data. Right. So why don't you go ahead? And I'm actually curious what people think. And because I think that MLOps is a nascent and emerging role. So there are probably multiple groups that one could imagine jumping in to this role. Let me share a screen. Let's see what people voted. Cool. All right, pretty interesting. Okay, cool. All right, so interesting. I think there are a lot of machine learning engineers, data scientists on this call. So I think many of you are eager to have yourself or your team, embrace this role. So I think that's great. I think DevOps engineers could certainly take it on. I see, less love for the software engineers in this vote. But I think software engineers are a little bit further. It's kind of like a two-step move rather than a one-step move. I think many software engineers could do it too. And I do see domain experts playing an important role, a very important role in MLOps, because often the domain experts, they understand, right, better than a non-domain expert exactly what is the appropriate label and how to debug that process. But I think different people from all of these roles could help with MLOps. All right, thank you. So I've just two more slides. Then I wrap up and take people's questions. Because a lot of AI had grown up in consumer software internet, companies have a lot of data. There's a lot of hype and excitement about big data. Nothing wrong with that. If you have a lot of data, that can be very helpful. But as AI breaks into other industries, especially ones where the data set sizes just aren't as big, I would love to see a shift. I think it'd be useful for many of us to shift our mindset from big data to good data. And MLOps, when we stand at MLOps, I think most important guiding principle is for the MLOps team to help ensure consistently high quality data in all phases of the machine learning project lifecycle. And so what is good data? Just like food, where it's not about maximizing the number of calories you eat, I think good data is data that is defined consistently. So the definition of the labels Y given X is unambiguous, covers the important cases. So do you have good coverage? Do you have enough data of speech with car noise in the background or any other important cases? Has timely feedback from production data. So, distribution covers data drift and concept drift, and is sized appropriately. And other issues that are a little bit more domain specific, in some domains where there are data governance issues, such as in healthcare, where, patient privacy, that has to be respected. In some problems, in a lot of commercial problems, the issues of bias and fairness, like steel defect detection, right? That's less social impact, but in projects with social impact, good data needs to address those issues, obviously, and be audited against fairness and bias standards. But I think that if we can, in the appropriate domain-specific way, which is different for different problems, have MLOps teams help us ensure that with good data, then all of us will really get machine learning projects to work effectively on a lot more problems, including ones where you have fewer than 10,000, or just smaller data sets, but also larger data sets as well. This is my last slide, then we'll go to questions. Takeaways I hope you will use, and this is the first time I'm speaking publicly about these ideas. I'm shaping them for over a year with some of my collaborators. But if you think these ideas are useful, please help me spread the word and help ship people to a data-centric AI. But takeaways, I think MLOps' most important task: make high-quality data available through all stages of machine learning project lifecycle. If we just do this, there are a lot of great models, open source models you can download off GitHub, right? You can find the code snippet you need on Stack Overflow. You usually can't find the data snippet you need on Stack Overflow or on GitHub, because data tends to be much more customized. So if we can ensure consistently high quality flow of data, then that together with the code, which is also important, can help us be more efficient in developing effective machine learning systems and deploying them and maintaining them. AI systems that code plus data. For a lot of projects, we tend to instinctually take a model-centric view. And when you are working on a project, I hope you also consider for your projects a data-centric view, where you ask how to systematically do error analyses, other types of analysis to figure out how to change your data to improve performance. And then finally, I think one of the most important frontiers of AI is going to be MLOps tools to make data-centric AI an efficient and systematic process. So it's not counting on the luck or skill of an individual engineer to spot the problem and figure out how to fix it, but for us to all have systematic frameworks of thinking to spot these issues and improve on it. I remember before modern version control, my friends and I, we used to write code and then email C++ files to each other as an email attachment, right? So, I will write a piece of code and then take the source file and attach it as an email attachment and send it to my friend and say, hey, I'm done editing the code. I won't touch it for the next 3 hours. Why don't you work on it? And then email it back to me when you're done. And then they'll do that. And then I will manually, merge their source code and my source code. So thank goodness we in the software community evolved towards version control, where we had like a CVS subversion and now Git, and that made it much more systematic. It feels to me that we are still in the emailing. So code management has become more mature. Data management goes beyond versioning. Versioning is one small piece of it, but ensuring good data goes beyond that. And it feels to me like we're still in the emailing stuff back and forth phase of how we think about data. But so I think this will be an exciting frontier for AI. And if we can make MLOps and data-centric AI more systematic and efficient, it'll help all of us be more efficient, effective in how we build and deploy AI systems. So thank you for sticking with me through this presentation. I'd love to see what questions people have. So if you go to this website, you can enter questions and then vote on the questions. Vote on the questions that you want answered. I'll spend a few minutes to take people's questions before we break at the end of the hour. So let me actually share people's questions. All right, cool. So thank you, Vishnu Rajan Tejus, for your question. How about hybrid approach of model-centric, excuse me, just some. How about a hybrid model of model-centric and data-centric development? Yes, I find that you don't need to be 100% data-centric, right? Sometimes you do want to improve the model. And in fact, there's a lot of cutting-edge research where we AI work, we do need better models. So it's totally great. It's great for people to keep on doing research and improving models. What I find is that because we as a community, we've invested so much in improving the models, for a lot of problems, I think is equally useful, maybe even more useful sometimes, to work on improving the data. And I find that for a lot of applications, the model is basically a solved problem. There's a model you can download off Git, an open source model you can download off GitHub that's good enough, but the data needs to be much more custom. But there's really nothing wrong with continuing to improve the model as well. All right, Jack asks, data so critical, but real world data is been ahead. What's best way to generate relevant synthetic data? You know, I find that there are some really sort of cool, exciting techniques like GAN data augmentation. And I've used that. And I find that those really exciting techniques is often one of the later techniques I will go to. So yeah, I find that there's often simpler ways than, the most exciting cutting edge, let's use a GAN to generate more data. But instead, synthesizing background noise in speech recognition, or image warping flips, or just going out to collect more data, they're often, it's very problem dependent, I guess. Maybe I'm stumbling a little bit because I think it's very application dependent. But I found that there are often ways to just collect more data or clean up the data. And then, eventually you might want to generate synthetic data, but it's usually one of the later techniques I will try. I have done it, but usually not as the first thing I try. They're usually simpler things to get high quality data and improve performance. But it is problem dependent. What do I think of BERT GPT? Boy, no ways to make NLP significantly better. Yeah, so I played with GPT-3 quite a bit, BERT a bit as well. Boy, I don't know. I think these are exciting technologies. I think BERT GPT. This is actually a good example of exciting algorithmic breakthrough, right? Attention is all you need. Transformers scaled up dramatically, became with other important details became BERT and GPT-3. I don't know. I'm excited about this line of research. What I find is that a lot of the practical problems people face today, how do you go to a healthcare system, build an AI to read the electronic health record? How do you go to a wheat harvester and build a computer vision system to figure out what's going on in the wheat fields? Or how do you, get computer vision to work in a manufacturing setting? Or how do you build an NLP system to improve product recommenders or search on an e-com website? There are a lot of problems where you don't need the 175 billion parameter model, but of course there's room for that too. Hopefully I'm answering the question. Thanks Max for the question. Yeah, I think that I think that there is insufficient material on MLOps out there. So I think we as a community collectively, I think MLOps is such a new field, right? We're still we're still developing the guiding principles for MLOps teams. So I think because it's such a new field, the amount of good materials on the internet is not large. But hopefully, because it's such a new field, I think it's been difficult for anyone really to create great tutorials. But hopefully that's something that the AI community can collectively work on. We've got to figure out how to manage data systematically, then share these practices. I think we're in the early phases of figuring out MLOps. What MLOps teams do? What MLOps tools do my teams use? Honestly, we end up doing a lot of custom things. Landing AI tends to build a lot of custom tools to manage the workflow for manufacturing. I think it's a very nascent field. Yeah, right. And sometimes we do build on top of the open source frameworks, right? Build a lot on top of TensorFlow, sometimes build on top of PyTorch. But I think these are great questions. Thank you, Paolo, for this question. I was excited to share these ideas with you because they're actually really new. I hope we can together shift how we approach machine learning problems. I have to admit, I wish there were more mature MLOps tools, around the entire world. But I was hoping through this presentation to start the conversation so that together we can all work on building better MLOps tools. So, but I think we build a lot of custom ones. And one of the things I found is that a lot of MLOps tools, I think, need to be verticalized. Rather than building horizontal platforms, so TensorFlow and PyTorch are great horizontal platforms, right? You kind of use them for, every machine learning application under the sun, maybe. But I find that a lot of the data practices need to be verticalized. So for example, if you're working on electronic health records, deploying stuff in hospitals, well, there's serious patient privacy concerns that need to be addressed, and also auditability and repeatability of the models you use. So the data management processes need to respect those practices that's specific to healthcare. Or your manufacturing, right? Landing AI's landing lens. Well, there are very specific terminology and concepts for manufacturing. So we built very custom things for that. Or take the financial industry. Again, you have very different set of considerations, safety, governance, financial regulations. So I think we'll see that a lot of the MLOps tools will have to be much more verticalized to respect the protocols, issues, data governance, fairness bias, things that are specific to that particular industry. So it'll be exciting to see vertical platforms arise. But thank you for that question. All right, Kirill asks, aren't government large corporations an inherent advantage given data-centric approach? Yeah, so I'll be very candid with you. There's one large company that I will not name, but there's one large company where I know that inside that large company, there was a deliberate decision to say, hey, let's go and tell everyone how important giant data sets are, because this will discourage competitors. Because, at least one large company had a explicitly discussed strategy to say, hey, let's tell everyone that you need a giant data set to do anything, so that, I don't know, everyone else can just give up and just work with us instead or something, right? So I think the big data hype, when you have a lot of data set, it's great, use it. It can be very powerful. But I find that there are a lot of problems where no one has that large a data set. So for example, even if you have a giant data set, of social media or internet search or online advertising, those data sets are not actually useful for, they don't seem particularly useful to me for diagnosing medical images or spotting particle defects on a sheet of steel. So data is very verticalized. There are a lot of problems where the data set size, is like, I don't know, 1,000 examples or 10,000 examples, and a small startup can have more data that's specific to that domain than a giant internet company, and thus a small startup can do perfectly fine with its data advantage in its domain, because web search data isn't actually useful, for I don't know, diagnosing from medical images, right? Not directly. So I think data is very verticalized. It's really data for your applications. I think there's actually lots of opportunities for smaller teams and smaller startups. All right, Ash Boy, I feel like Fan asks, what do you want to train large models like Transformer? Yeah, so I've often been surprised at how well we can build a system with like 100 training examples, right? But again, the key is, turns out if you have 100 examples and 2 of the examples are noisy or 5 of the examples are noisy, that's a big fraction of your training set. So we have 100 examples, really important to make sure your data is as clean as possible. And I've frequently been surprised, right? Train an algorithm on 50 or 100 examples and it works. So it is possible for some problems to do that. All right, let me just take last couple questions. I should break. Clean data, crucial to background knowledge. Yes, in fact, I think that good data practices is a good way in order for domain express the background knowledge. So I think this is having good practice is a good way for domain express the knowledge. Let's see. Yeah, I don't have information about this at this time. Sorry, TL. All right, last one. What do you see most potential tech-related MLOps leader in MLOps early? I think it's very early. The sector I'm excited about, but I think there are lots of teams trying to figure this out. But if we can have the field take a data-centric approach to MLOps, and just remember, I think the most important task of MLOps is ensure consistently high-quality data throughout the entire life cycle of machine learning project. We can build tools to make that happen in different domains. It'll be different for different domains, then that will help machine learning move forward. All right. Hey, thanks everyone for all the questions you asked. I think lots of great questions. I'm sorry I don't want to run past the hour, but I hope you will help me spread the word about data-centric AI and MLOps, and I hope some of these ideas will be useful to you as you're building your machine learning system. So thanks for joining me today to chat with me about these ideas. It was nice to see you today, and I hope we'll have other opportunities.